あ、それはゴミです。ゴミです。書類はゴミって言っちゃいましたけど、別にゴミじゃないです。あげるための口実だって。お礼ですよ、お礼。ちょっと営業していきましょうかね。公園。
So there are two components of this one request batching. You're going to actually use the link in the but request batching, you have it within that schedule. So request batching is pretty simple, right? How do you actually implement it if you're working with it? You can actually add a single bit associated with each request, say, is it part of the batch or is it not part of the batch, right? We'll call it the mark bit. And the batch formation is a relatively simple process. We're going to mark up to some number of all those requests per bank for each bit. We'll call it marking cap. So this will lead to some trade-off actually in the design. And these mark requests constitute the batch, and the memory store forms a new batch when there's no mark requests left. And mark requests are prioritized over unmarked ones. As a result, you get most priorities and hopefully high fairness. Coherence will be dictated by your schedule also, but this enables some basic level of fairness. Because there's no reorganizing across the batch. So the only key question is how do you prioritize requests within a batch? Now, the batching provides a substrate for non-priorities and fairness, priorities and non-fairness. How you reorder internally, we have to make the difference. So if you simply use any existing EF schedule policy, right, within the batch you can say I'm going to use that RGFS, which is good for rollover locality. But you also want to preserve each other's background. Remember that was our motivation to begin with. And for this, you really want to service each thread request back to back. So to be able to do that, the schedule will use a ranking of threads when the batch is formed. And the higher rank threads are prioritized over lower rank. The hope is that if you do this ranking well, this improves the likelihood that requests from a thread are serviced in parallel by different banks. Because if you do the ranking for both banks, the ranking for parallel, but it's not the best for performance and fairness. And the ranking could be many sets of threads last, many nine sets of threads first. Why would we say just because threads many nine intensive? If you say that's fewer requests. It's likely that if you service those requests, it's going to go back to score and go on computation. That's going to make it utilize score. Whereas if the threads many intensive, it's going to slow anyway. So it's not going to utilize score. So the service these many non-intensive threads, you get better quality filtration in general. So we're going to do something similar to that in a more complicated way. Basically, let's look at the thread ranking idea over here. You have the thread A and thread D, and you have these two different things. If you don't do this ranking, basically both of those threads will work through 10 times the sequence. Now if you do this ranking, basically the service order looks like this, and you get going right over here, like this is like. So ranking scheme affects actually what system improve that fairness. So your goal, the goal is to maximize system improvement, not minimize on-fairness, or maximize fairness. And this is equalize flow down threads. So how do you actually, what is the goal for, how do you maximize system improvement? Basically, you want to maximize the average flow time of threads, right? Remember the graph that I showed earlier? By preserving parallel, you reduce the flow time 1.5 times extra space as opposed to 2 times extra space. So you really like to minimize the average flow time of the threads. To minimize unfairness, basically you like to service threads that have inherently low flow time broken into batch. Every non-intensive thread broken into batch. Right? Because if you delay every non-intensive thread, it results in high slowdown. So consider the case, your baseline slow time of first thread is 1, for another thread is 4. The second one is very intensive, the first one is not that intensive. Because it has fewer requests, that's why slow down is 1. Now if you delay that by the same amount, let's say by 1 unit, the first one slows down by 2, right? But the second one slows down by only 5%. It'll be 21 over 20. That's the inside over here. You really would like to prioritize the thread that has fewer memory requests if you want to slow slow time. So basically, shortest slow time or shortest down first ranking, I can achieve this. Shortest down first actually.
Whatever.
Not a single server rank, you have multiple banks. That's kind of messed it up. And you have a rollover. Sometimes you mess up your flow. But still, here applies here also. Except we were having everything else now. Basically, to control that, each thread's slow time within the batch, and rank threads with shorter slow time by. That's the idea over here, to be able to satisfy both of these. So let's take a look at how this can get implemented in hardware control. In fact, this implementation is a little easier actually. Basically, the controller is going to keep track of two values. One is the actual number of mark requests for any banks. Remember, we're talking about within that schedule. That's why everything is marked locally. And this goal is